Hi, I'm Zor. Welcome to Unizor Education. I'm going to talk today about planet's orbit, primarily the geometry of the orbit itself. We all know that this is ellipse, but what kind of parameters does this ellipse have? So, first of all, there are some prerequisites to this lecture. This lecture is not just by itself, it's a continuation of actually many lectures preceding this, where I was talking about Kepler's laws, about certain properties of ellipse, etc. Now, every lecture in this course has notes, and they're all presented on unizor.com. So you have both lecture and the notes for it, and in the notes I have some additional information, like for example what prerequisite lectures is necessary to be familiar with, at least the material which is in those lectures. Maybe you got it from somewhere else, but in this case again I will use certain information which I have already conveyed in the previous lectures. So it's all presented on unizor.com. This is part of the course called Physics Plus for all. Well, one of the preceding courses was Physics for Teens. Now this is for all, and this is a little bit more than for teens. What else? Now, as I said, every lecture has notes for it, very detailed notes. Now, in this particular case, I might actually have some shortcuts in my different derivations, in which case I will just address you to the notes. For example, I have some quadratic equation which I'm not going to solve here. I'll just write the result, and if you want the details you can have it in the notes, unless you can obviously do yourself this plain quadratic equation. Okay, so let's start. So we are talking about planet orbit geometry, and I would like to start with not geometry of elliptical orbit, which we will go through a little bit later. I would like to start with the geometry of a circular orbit. It's much simpler, and I am going to derive certain things which will be very useful with elliptical orbits. So if we are talking about circular orbit, we have let's consider it's a planet around the sun, just to have it in mind. Obviously you have two different laws which basically dictate how this planet is moving around the sun. So first of all, this is Newton's second law, and secondly this is the universal law of gravitation, where m is mass of our planet, capital M is sun's mass, g is the universal constant, very small one by the way, a is centripetal acceleration of the planet, and r is the radius of rotation. So we do have this. Now I would like to express certain relationship between the radius and the linear speed of the planet on the orbit to basically to stay on this circular orbit. Okay, so let's consider we have some Cartesian coordinates with the sun being in the center, and the xy plane where the planet is actually circulating would be xy plane. Now, considering this is a uniform movement, so we have r, which is constant, right? It's a constant radius, it's a circular movement, and also we have constant angular speed omega. Okay, so let's try to find the relationship between these. Are the same forces, right? So basically this equation I would like to somehow simplify. Well, obviously I can cancel m, so I will have A is equal to gm divided by r squared. Okay, so this is very important thing. It's a constant centripetal acceleration which depends on the radius and some constant, basically astronomical constant, which is mass of sun times now obviously it's not only sun and planets, it's obviously between two different bodies which have mass. One of them is fixed in space and another is circulating around it. But I will use sun and planet as just terminology, basically. All right, so let's talk about coordinates, xy coordinates of the planet. Now, considering we have this circular movement, so from the top it looks like this. This is the sun and this is the planet. So obviously this is x, this is y. X is equal to r times cosine theta. This is angle theta. And y is equal to r sine theta. Now, from this I would like to derive the linear velocity and centripetal acceleration. Now, velocity is tangential and centripetal acceleration is towards the sun. So to get the velocity, I just have to differentiate them, and velocity will be square root of x squared plus y squared. So x first derivative by time is equal to, so the only variable here is theta, right? Theta is basically x of t and theta of t. Now, also, let me just a little bit simplify it. It's equal to r cosine omega t, and this is r sine omega t. So if omega is angular speed, then it's uniform rotation. So by time t, we will cover the angle omega times t. Very noisy. Okay. So the first derivative this is x component of the velocity. Derivative of this is r is constant, omega is constant. So it's basically cosine, derivative of a cosine, which is minus sine, and derivative of internal function, which is omega t, which is omega. So it would be minus r sine omega t times omega. And the y component of the velocity would be the derivative of sine as a cosine, so it would be r cosine omega t times omega. Now the second derivative, that would be for acceleration, would be derivative of this. Omega is constant, r is constant, so it's all only sine. So from sine, derivative is cosine, so r. Minus r cosine omega t, and now it will be omega square, right? Omega plus another omega. And the second derivative of y component would be minus r sine omega t times omega square. Now, if I need acceleration a in this particular case, what is acceleration if I have acceleration by x and by y? That's basically square root of x square plus y square, right? Square. Because these are components of the vector. So the length of the vector, which is the magnitude of acceleration, and this is equal to what? R square omega square. All right? Because cosine square plus sine square would be equal to 1. So under the square root, I will have r square omega to the fourth and r square omega to the fourth times cosine square times sine square. So they will be the resulting r square omega to the fourth, and the result would be r. Okay, equals 2. Now again, since my linear score, my linear speed is equal to radius times angular speed, then I can say that this is equal to v square, which is r square omega square, divided by r. Because it will be r square, I need only r. And this is equal to gm divided by r square, from which follows r squared divided by r would be r, from which follows r v squared divided by gm equals to 1. Okay, so this is the formula which I wanted. This is a relationship between initial radius and initial velocity, linear velocity. It should be equals to g times m, the gravitational constant times the mass of a central body, like in Sun, for instance, case, which produces the field. It's not related to mass, by the way. Mass is cancelled out from the very beginning. So for any planet, if its speed and velocity are of this type, that is a necessary condition for being in a circular orbit. And apparently this particular ratio is very important for elliptical orbit as well. So I will have a special symbol for this. It's equal to beta. I call it beta. Don't ask why, just beta. Okay? So this is all about circular motion. I have introduced this particular term, this particular ratio between rv squared. This is radius and this is the speed. And for circular orbit, it's supposed to be equal to 1. Now, let's just put it this way. Consider you have a central body which has certain mass and gravitation, and from some initial position you basically shoot some kind of an object, a planet, whatever, with certain initial speed, let's put it v0, and on the radius r0. Only in case this is equal to 1, only in case the product of radius times times speed square divided by gm, where m is the mass of this body which is in center, only then the orbit will be circular. If it's less than this particular, if this ratio is less than 1, so if, let's say, r is fixed and you're changing the speed v, so if the speed is this one, you will have circle. If speed is greater, it will be probably something further. It will be ellipse, kind of an ellipse like this. If it's slower than this particular, then it will be another ellipse. So basically it all depends, the shape very much depends on this particular coefficient which I call b. Okay, so that's it for circular. Let's go to elliptical orbits. But do keep in mind that this is really very important, how v and r are related to g times m. Okay, so let me put this thing over there. Beta equals to r0 v0 squared divided by gm, and for circular it's equal to 1. Okay. Now let's go to elliptical. First of all, what kind of elliptical characteristics we are interested to know the geometry of the ellipse? Well, first of all, again, one of the prerequisites was about the ellipse, which I have addressed it in mass plus course for all. So basically there are a few different parameters. First of all, there is a major axis which is 2a, so semi-axis is a. There is a minor axis which is 2b, so minor semi-minor axis is b. Now there are two focal points and this distance is c. And also there are certain relationship. For example, c divided by a is called eccentricity of the ellipse. C divided by a, that's eccentricity. Now the a and b and c are related because this is supposed to be 2a, so this is a and this is b. So b squared plus c squared is equal to a squared. So this is all addressed in the lecture about ellipse, and you can just refresh it. But these are very simple characteristics of the ellipse. So I'll just have it in mind. So these are the characteristics which I have to really find if I'm from some radius r, I'm shooting the planet with the speed v0, and I would like to know, well, if it's equal to 1, it will be circular, but if it's not equal to 1, I would like to know what kind of an ellipse will be. So what kind of semi-major and semi-minor and axis and eccentricity of the ellipse. I would like to know these characteristics based on initial condition of the movement. So if the planet is moving around the sun in an elliptical orbit, I would like to fix one point, check what's the radius and what's the velocity in this particular place, and derive all other characteristics, these characteristics, from these two initial parameters. Okay? All right. So, first of all, which point to take? Well, we know from the first Kepler's law that the planet goes around the sun on elliptical orbit, and the sun is supposed to be in one of the focal points. So let's say this is the sun. Now, it's very convenient to choose as the initial point one of the good points, let's say, on the ellipse. The good points are something like this, for example. Well, I didn't really do it correctly. It's supposed to be a little bit better, something like this. Why? Because if this is the radius, and speed would be perpendicular to ellipse, perpendicular to semi-major axis, because it's supposed to be tangential, and if you have a semi-major axis, the tangential will be perpendicular to it. It's just symmetry of the ellipse. So it would be easier. So I have chosen this particular moment in time and place on the orbit. So it will be t is equal to 0, and it will be r0, which is distance from the sun, which, by the way, equals to a plus c. So r0 is equal to a plus c, but just keep it in mind, doesn't really matter right now. And the speed, which is vector velocity, will be perpendicular, and the speed itself, absolute value, the magnitude of this vector would be v0. So we consider them as given, as well as mass of sun and gravitational constant, etc. So in terms of r0, v0, and m, well, and g, I would like to express geometric characteristics of my ellipse. Okay, good. So we know what we want to do. So first of all, the equation of ellipse has been derived, and basically equation is this is r depending on angle theta in polar coordinates. So we have chosen polar coordinates with the pole at sun, with the base axis of polar coordinate to coincide with semi-major axis, And moment t is equal to 0 is when our planet is, this is actually the furthest from the sun point, which is called, by the way, aphelion. So that's my initial position, and initial radius would be from sun to this point, aphelion, and velocity would be perpendicular. So it's all given, and we have started, and now we would like to basically move on. And now again I would like to use the equation of the ellipse in these coordinates, and it will be r of theta, which is length of this from pole to any point on ellipse, equals to let me just a1 minus e squared divided by 1 minus e cosine of theta. So this equation of ellipse. Again, I have addressed this in the proper in the lecture about the ellipse, and the reference is in the notes if you wish. But I do consider it as known and given. Okay. Now, so what happens if I put theta is equal to 0? My point is here. So my r of 0, which is r0, it's given, right? This is given. And it's supposed to be equal, cosine of 0 is 1, so it would be a times 1 minus e squared divided by minus e, so it's a times 1 plus e, which is basically a plus e is by definition c divided by a times a, so it would be a plus c. As we know, it's a plus c. So that's correct. Anyway, so I decided to concentrate first on two parameters, a and e, because parameter c can be derived. If c divided by a is e, then c would be equal to a times e. Knowing c, I can derive with a semi-minor b. Okay. But we have two different unknowns, a and e, and only one known, r0. We cannot solve it. We need more. Okay. Well, let's put my point here. So angle theta would be equal to pi, 180 degrees. So what happens? In this case, cosine is equal to minus 1. So it would be 1 plus e. So the result would be r of pi is equal to a1 minus e. So we have two equations. Unfortunately, we have the third unknown. Okay, so what do we do? Okay, now what we do is the following. We have two very important theorems about the angular momentum, conservation of angular momentum, which is the basically something which is proven for any central field. There is a corresponding lecture about this in this course. And we have energy. So conservation of energy and conservation of angular momentum give us another equations which we need to basically find out what's r of pi, this little thing, which is supposed to be a minus c actually, but doesn't really matter. It's the same as this one. All right, so what do we know about angular momentum? Angular momentum in this particular case, L is equal to m times r times v. These are vectors. But these vectors are perpendicular to each other in both cases, this and this, because in this case speed is this way, and vector of position is this way. In this case, it's also perpendicular. So the absolute value of L is equal to m times r times v in both cases. So, considering we have a conservation of momentum, L of 0 should be equal to L of pi. Right? So, m would be the same in both places, so r of 0 times v of 0, which is r0 and v0 given to us, should be equal to r of pi times v of pi. Okay, so this is an equation for r and v. So how many equations do we have? We have one equation, we have two equations, and we have three equations. How many variables? A, E, r of pi, and v of pi. So we need one more. We have four different unknown. The next one would be energy conservation. Now, energy conservation is kinetic mv squared divided by r squared of pi. Now, that's the kinetic energy. The potential energy is g times m divided by r of pi. Potential energy has a minus sign, and it's measured in that's how potential energy in gravitational field actually is. So we can always you can always again refer to the gravitational field and potential energy. It's all presented in the physics course, so I consider this as known. And it's equal to, so this is of pi, and this is the same thing supposed to be for 0, angle 0, so which is m v0 square divided by r0. Wait a moment. No. mv squared divided by 2. What am I writing? This is kinetic energy divided by 2. Minus gmm divided by r0. Okay, now that looks much better, right? Alright, so from this obviously we can get rid of mass of the planet, nothing depends on it. And what we have right now is the second, the fourth actually equation. So we have these variables. So what do we do then? Well, first of all, we resolve this for v of pi is equal to r0 v0 divided by r of pi, and we substitute it into this equation. So we will have one less variable, and correspondingly we can find from this equation, only from this equation, we actually can find r of pi. Now, I'm jumping over these trivial calculations. They are presented in more details in the notes for this lecture, but I'll just write what will be the result if I will substitute this into this equation and solve it for r of p, r pi. Now, by the way, what will be a quadratic equation, because this goes square, right here, this is a square, so I will have r squared of pi in the denominator. This is plain r of pi, and there are no r of pi here. So I will multiply everything by r of pi squared, and I will have a quadratic equation with certain coefficients, and I will basically resolve it. It's a simple thing, just a little bit tedious, but the problem is that the answer is relatively short and nice. So let me just write the answer, which is the result solution to this quadratic equation. R of pi is equal to r0 times beta divided by 2 minus beta, where beta is this coefficient. So that's why I have actually introduced it for circular movement, because it's very handy, because now solution to this relatively complex ugly looking quadratic equation would be relatively simple formula. And from here, now I can actually derive everything which I need. Let's recall. My R of 0 is equal to A 1 minus A 1 plus A, and R of pi, which is equal to A 1 minus A. Okay? But now I know what this is. It's R0 beta divided by 2 minus beta. And beta is known. So from here, again, using the beta as a kind of abbreviation for an ugly expression, I can very easily derive both A and E. So again, this is just a system of very simple equation. If I will add them, I will get to A, right? So my A is equal to 1/2 of R0 plus R pi, which is R0 plus R0 beta divided by 2 minus beta, 2R minus R plus R, so it's and 1/2. So it will be 1R, which is R0 divided by 2 minus beta. Okay, I've got my A. How to get E? Well, if I will subtract it, I will have A plus AE, A minus AE. If I will subtract it, I will have 2AE, which means if I will have the difference between which is R0 minus R of pi, and divided by their sum would be equal to 2A, I will have E. Now, and here I will have a very interesting thing. If you will put everything in this formula and simplify it, basically, will be a very nice thing. 1 minus beta. So that beta is very much related to eccentricity. So like beta is equal to 1 minus eccentricity. Now we know that the beta for a circular is supposed to be equal to 1. Now 1 minus 1 is 0, so eccentricity of the circle is 0. And it means basically that these two focal points are closer and closer together, and in the circular both are the same. So C is equal to 0, and therefore A, which is C divided by A, also is equal to 0. So eccentricity of circle is 0, and this is just confirms this particular observation. Now, what else do we need? We need C. C is our focal semi-focal distance, and that's easy. That's A times E. So you will multiply them by each, and it will be C is equal to R0 1 minus beta divided by 2 minus beta. This is A, and this is E, right? So that's formula for C, and finally formula for B. B since B square is equal to A square minus C square, B is equal to, I'll give you just the result, R0 divided by 2 minus beta, square root of beta times 2 minus beta. So we have formulas for A, B, C, the semi-major, semi-minor, the eccentricity of this. So basically all the geometry we have found, which is fine. Now the only thing I would like to add is area. Now area, again, area of the ellipse, we know about this, A times B. It's one of the lectures, by the way, about ellipse. So from here we can derive the area, and the area is equal to pi r0 square divided by 2 minus beta square and square root of beta 2 minus beta. So this is all geometry of the ellipse in terms of r0 and v0 and mass of the sun. So initial distance from the sun in the aphelion position, the furthest from the sun, and initial velocity, which is perpendicular to this direction to the sun, completely define the geometry, and that's what it is. So read the notes for this lecture. I do recommend you to do this, and basically that's it. Thank you very much.